The sun changes. It just takes a long time for it to do so. Since its birth, the sun has grown steadily brighter. When it all began, the sun was only producing about 70% of the output that it currently is. This is an understood process in astrophysics. Essentially, the sun is fusing up its hydrogen in the core, resulting in helium. And that causes very gradually over time the core to become denser and hotter. Fusion increases as a result, and the sun brightens. This slow process is seen in observations of younger stars, and eventually this process will get to a stage where Earth cannot handle it. The oceans will boil away and eventually the surface goes molten. That will be the final extinction event for life on Earth, unless it leaves Earth. This process will begin in about 1 billion years, when the sun has an additional 10% output. This is all well understood stuff. The physics of it are very straightforward. But there is a mystery hiding in the whole thing. First noticed by Carl Sagan and George Mullin in 1972, the faint young sun paradox states that if the sun were 30% less luminous during the early days of the solar system, then Earth should have been frozen solid. Yet it apparently wasn't, and life, very dependent on liquid water for its chemistry, managed to get going. This paradox has never been resolved over 50 years later. What's clear is that it probably was not due to anything unexpected with the sun, but rather somehow Earth had some attribute that warmed it during that period that reduced later. Potential explanations include greenhouse effects from a lot of carbon dioxide, changes to the planet's albedo, and numerous others, including astrophysical effects, such as different cosmic ray profiles hitting Earth. The bottom line, though, is that we don't know exactly what happened. As an aside, the faint young sun paradox isn't limited to Earth. Mars and Venus were also affected here, and with Venus it should have resulted in the surface of that world being about perfect for liquid water oceans. Again, we don't have a great handle on Venus's early atmosphere, but it may have been an ocean world. But where it really gets strange is Mars. That planet should most certainly have been frozen solid early on, yet it shows evidence in droves of the activities of water between 4.1 and 3.7 billion years ago, ranging from outflow channels, riverbeds, modified craters, and basically everything water does. Yet if it was hard for Earth not to freeze, Mars is further from the sun, and the paradox is even greater. The best answer is a greenhouse effect. A dense atmosphere made up of mostly carbon dioxide and probably another gas like methane or hydrogen is a candidate. But so little is known of early Mars and its conditions that it cannot be said for certain. And there are certain problems with Mars actually retaining enough CO2 in a carbon cycle to have produced the warming effect that was needed. But add in a lot of volcanism and maybe it accounts for it. The paradox aside, the sun will change again, long after life in the inner solar system goes extinct or has to move. Eventually it will hit its red giant phase and swell sometime around 5 billion years from now. The sun's core will continue to contract as it runs low on hydrogen, and the heat will rise until it becomes hot enough for the sun to fuse hydrogen in its outer envelope, and the red giant results as the new equilibrium for the star. This will be the destruction of the inner planets, though it's unclear whether Earth will get swallowed by the sun or just get scorched into a cinder. After the red giant phase, however, comes yet another phase, a very long-term one, that of the sun as a white dwarf. White dwarfs are a kind of outlier when we discuss stars suitable for life to arise around, because they are not main sequence stars anymore. They are cooling but very hot remnants of stars that take enormous amounts of time to radiate off all their heat. As far as habitability goes, this actually provides a very stable energy source if you're close in. And while it's hard to imagine life surviving the creation of a white dwarf, habitability itself can be imagined. The big problem is a planet surviving the death of its star. So while the inner planets are in trouble during the red giant phase of the sun, the outer planets and moons will be in a better position depending on where they are. Anything about the position of Jupiter and outward might be in a decent position to get warmed up and melt during the red giant phase and become surface ocean worlds. This is actually a rather creepy scenario, but worth speculating about here. So the actual extent of the red giant phase is not well understood. It's not clear how big the sun will become exactly, and we just have an approximate number. which is why no one can say definitively if Earth will get swallowed or not. Those uncertainties also govern just where the habitable zone of the red giant sun will be located. But there is a solid chance that the Jupiter system will be prime real estate, and that means Europa, Ganymede, and Callisto could melt, and for a time exist as surface oceanic worlds. And this is where things get murky. All three of those moons are suspected of having subsurface liquid water oceans right now. They are ice shells. Go deep enough and it becomes liquid. But what's unclear is how long those oceans can last, because it's dependent on tidal heating and radioactive decay, which lessens with time. But if tidal heating is enough, which it probably is for Europa at least, then those moons conceivably may go directly from ice shells to surface oceans without ever freezing solid completely. If that's the case, and any of those moons have life, Europa being a decent candidate, as is well known, then that microbial or even macroscopic life would be freed from its ice shell to do whatever it may, as far as evolution goes, for a time at least in the far future during the red giant phase. This is such an enormous amount of time that if life hasn't arisen on those moons yet, it has billions of years more to do so, if it is indeed possible. Or if it's not possible right now, it may become possible when their surfaces go liquid. Granted, there are a ton of what-ifs and maybes involved in that, but it's interesting to think about in terms of our solar system, but also red giants of this type in general as habitable stars in the universe, something not well discussed at this point. Eventually, however, the red giant phase will end as fusion ceases, and the sun's outer layers are expelled into space, and what remains is the former core as a white dwarf. As a result, white dwarfs are very tiny, about half the diameter of Earth, and very, very hot. Because they're small, they don't radiate heat rapidly. But it actually is enough for a habitable zone. A liquid water planet would need to be extremely close to the white dwarf, about 1% of the distance Earth is to the Sun, less than 1 million miles from it. That's right on top of that dwarf star. And that makes this situational because the earlier red giant phase of the star would have destroyed its inner planets. That means any planet in that position will have to migrate there. And that's where things get iffy for oceans because the conditions for liquid water are very tight. One wrong move and you freeze over or your ocean evaporates. It is, however, possible in principle to happen. Known as tidal migration, this means that some dynamical instability among the planets of the system, which hosted a changing star, can toss a planet into a high eccentricity orbit, really elliptical, like a comet's orbit. That brings it really close to the white dwarf during part of its year, then very far out during most of its year. This is temporary, however, as the gravity of the system will circularize the planet's orbit right in the zone needed for liquid water. Again, very situational, but could happen. But there's an interesting feature here. These would be among the easiest exoplanets to study for biospheres by observing transits across the face of the white dwarf. Now there is a caveat here. White dwarf planets in general appear to be rare. There are only a handful of candidates, 2 of which JWST recently studied, and they do not transit. But in principle, as a white dwarf exoplanet transits, then the spectrum of its atmosphere should become easily visible, because not a whole lot happens once a star becomes a white dwarf. It's basically featureless, meaning that the atmosphere in question is much easier to weed out from the light of the white dwarf. Going from there gets even more interesting because it's been shown that JWST actually could detect water vapor and oxygen on a white dwarf habitable world. Another advantage here is that because white dwarfs are so small, the transit signal of a planet is much clearer and greater than with a main sequence star. Basically, this is the low-hanging fruit of studying exoplanet atmospheres, habitable or not. Whether some body in the solar system could do this in the far future is unclear but seems improbable, unless we do it artificially. If we survive into the far future, we will need to address the increasing luminosity of the sun in a matter of just a few 100 million years from now. But it is possible to migrate Earth using repeated, very long-term asteroid passes of Earth. We simply set asteroids on trajectories to pass close to Earth in their orbits, and slowly move it outward as the habitable zone migrates. What could go wrong with thousands of asteroids passing close to Earth? That aside, it physically is possible to migrate Earth as the sun slowly changes and be in a decent position for the red giant phase, and then more aggressively migrate Earth inward until it's right on top of the white dwarf. But this only buys you 20 billion years or so because eventually even the white dwarf goes black and stops emitting energy. We do not currently have any black dwarfs in the universe, however. It's not old enough to have produced them yet, so it remains a future hypothetical object. But standing on a firm basis of physics, they almost certainly will exist. And they're essentially the end point of the sun as an energy source. To keep going, we'd need to radically alter Earth with an artificial star of some type, or abandon it entirely, a frozen relic of our origins, and move to another star system entirely. A red dwarf or orange dwarf are the obvious choices. But there's also the option of another white dwarf, or even a black hole. As a result, white dwarfs seem to be ignored targets for SETI searches, even though in some ways they might be desirable for an alien civilization to colonize. But it also opens up the possibility of aliens specifically choosing sun-like stars, type G that can't go supernova, of a young age, because one takeaway from all of this is that it means that the sun, over the course of almost its entire lifetime as a glowing object, will have supported some form of habitability, regardless of the stages of its life it went through. Thanks for listening. I am futurist and science fiction author John Michael Godier, currently concerned about the sunglasses and sunblock supply for humanity in a few 100 million years. We're gonna need a lot of it, and be sure to check out my books at your favorite online book retailer and subscribe to my channels for regular in-depth explorations into the interesting, weird, and unknown aspects of this amazing universe in which we live.